Assalamu alaikum and good morning. I would just like to correct a mistake on page 2. Well, this is not in your notes, but I asked you to copy this down. Okay, so when we talk about oxidation or reduction, we can look at it in terms of oxygen loss or gain, hydrogen loss or gain, electrons loss or gain, and the change in oxidation number, whether they increase or decrease. The statement I made about this reaction between copper and H2O to form copper oxide and hydrogen gas, it was written as oxygen that has been reduced. Actually, it is the hydrogen in H2O. Please change that. The hydrogen in H2O has been reduced because water has lost its oxygen. Another way of looking at this is by looking at the oxidation number of your hydrogen. Each hydrogen would have an oxidation number of +1 in H2O, but since you have 2 lots of it, we would just multiply it by 2. When it is reduced to hydrogen gas H2, both the hydrogen atom would have an oxidation number of 0. Just multiply each atom by 2. So each atom represents 0, an oxidation number of 0. Moving on to this question on page 2 of your notes, example 2, question C. It should be an A plus and Cl minus. I've already told you about this, but there is also an issue with this question because it is debatable. Actually, some would say that this is a redox reaction, but some disagree. Okay, so for now, I would just like you to label that this example is ambiguous. So that means it's not clear. All right, you don't have to worry about that. As long as you know how to count the oxidation number of an element in different species, you should be fine. Moving on to section 2.2 on page 3 of your notes, writing balanced half equation. I have mentioned to you in the previous lesson that half equation is when you break down your full equation into 2. When you separate your full equation into half oxidation and half reduction. So for a reaction to have a redox, it means that both reduction and oxidation must be present in the same reaction at the same time. So we're now going to look at the half equation so we can focus on just the oxidation bit or just focus on the reduction bit. In the previous years, half equations are actually given to you in your data booklet of page 82 of your data booklet. So these are a list of half equations that you do not have to memorize. They're all given and it is all written as reduction. It's a reversible arrow, so it's up to you whether you take the forward reaction, that's your reduction. How do I know that? Because my electrons is on the left. That means I am gaining. Reduction is gain of electron. If you want to write down the oxidation reaction, you start from the right to the left. That means you take the backward reaction. So here you can see that silver will be oxidized into silver plus. In the process, it loses electrons. Okay, so I'm just going to teach you briefly. If you don't have access to these half equations, as you all know that in your exam, you won't be getting a data booklet given. So you're only given information that is necessary or needed to answer a particular question. So it's worth learning how to write down half equation. Half equations, just like your normal equation, must be balanced in terms of charge and number of atoms. So there's nothing different from writing down a normal equation. If the substance that is being oxidized or reduced contains a varying amount of atoms, then the half equations can be balanced by adding H plus, hydroxide ions, and water. You can either choose 1, 2, or none. In some cases, you would need to add any additional species or molecule. You just need to add electrons to balance it. Okay, so to balance atoms, of course, you need to add atoms, whether it's in the form of ions or in the form of molecule. But if you want to balance electrons, usually, if you want to balance charge, usually we just have to add electrons. Remember, we can only add electrons whether you add on the left side or whether you add on the right side. You will not add protons or any other charged species. Okay. All right. So let's have a look. You are required to write down the half equation for the conversion of a zinc solid into a zinc 2 plus. We count the atom of zinc as it is. Even though this is an ion, we count it as like an atom. So I have one zinc on the left, one zinc on the right. That looks balanced. Remember, this is just half equation. So I do not need to write down the other reactant. I am just focused on the species that is being either oxidized or reduced. I'll tell you this later. Now we only have a choice to add electrons. How many electrons? That's up to us. Okay. If we look at the charges on the left side, zinc is neutral, so my charge is 0. On the right side, I have zinc 2 plus, so my charge is +2. Electrons have a negative charge, so you need to think about where you can put your electrons so that your negative charge so that negative charge can balance the charges on both sides. Okay, I hope you can see that if I add 2 lots of electrons on the right side, that means plus minus 2. Okay, why do I need 2 electrons? Because 1 electron is -1. So 2 electrons minus 2. So if I have +2 minus 2, maybe I'll just write down like that. They cancel out. It becomes 0. Now my half equation of the oxidation of zinc is complete. How do I know it's oxidation? I have lost electrons. Another way to spot this is I go from 0 oxidation state in zinc solid to +2 oxidation state in zinc ion. My half equation is complete. So just some explanation. Add 2 electrons to balance the charge on both sides of the equation. If I were to show you, this equation would be given, they're arranged alphabetically. So if it's zinc, you go to the very end, okay? Zinc will be oxidized into zinc 2 plus 2 electrons. If you get access to the data booklet, that's great. You don't have to think, you just copy it down. Now, why am I taking the reverse? Because forward is the reduction equation and the reverse is the oxidation equation, and they are reversible. Next, MnO4 minus to Mn2 plus. So I'll just give space. First, count my atoms. We'll leave the charge to the very last. I've got 1 manganese on the left side, 1 manganese on the right side. Done. Manganese is done. I've got 4 oxygen on the left side. That means I need 4 oxygen on the right side. Now, I cannot just add oxygen simply by adding O atom. That is not stable. To balance oxygen, I add water. And since I need 4 oxygen atoms, I will need to add 4 H2O molecules. Now, introducing water will cause my hydrogen to be unbalanced. Okay, so I'll just add that. Count atoms, Mn balance. Secondly, oxygen is not balanced. Add 4 H2O to balance oxygen atoms. Next, hydrogen atoms not balanced. And to balance hydrogen atoms, I need to add H+, not H2, not H atom, and nothing else. You just add H+. This means that the reaction is happening in acidic condition. If I count the number of hydrogen on the right side, I have 8. On the left side, I have nothing. So I need to add a H+. Only add H+, right? Check again. Mn, 1 on each side. Oxygen, 4 on the left, 4 on the right. Hydrogen, 8 on the left, 8 on the right. Atoms done. Lastly, check charge. We'll start with on the left. On the left, I have -1 plus 8 times of +1. So that means -1 plus 8. So in total, that is 7. Whereas on the right side, I've got +2. H2O is neutral, +0. If I total this, +7. +7 on the left side, +2 on the right side, that means it is not balanced yet. I can only add electrons to balance it out. So you have to think which side will help this equation to be balanced by adding electrons. So what I can do is add 5 electrons on this side so that I now have 7 minus 5 to give +2. Is that clear? And that is in fact the half equation for the reduction of manganate ions. This is not a full equation, so I do not have an oxidation happening in this reaction. Only manganate ion in the presence of an acidic condition is reduced to manganese 2 plus. I go from Mn would have an oxidation number of plus 7. -1 plus 8. Yeah, plus 7. Okay. So just label this as charge on the left, charge on the right. If we're talking about oxidation number, Mn is plus 7 in MnO4 minus, and in Mn2 plus it is plus 2. You notice that manganese has gone down from 7 to plus 2. That means this is a decrease in 5 units. And that is also the same number of electrons that you gain in order to reduce the oxidation number of manganese from plus 7 to plus 2. You need 5 electrons. So it all works out nicely. Okay, if you need to copy this down, you can pause. I will show you, this is also given in the data booklet. MnO4 plus manganate ion plus 8 hydrogen ions plus 5 electrons to form Mn2 plus 4 H2O. So again, I repeat, if you get access to the data booklet, you do not have to work this out. Do not waste your time working it out when the equation is given. Okay. Next. So that's just the same thing that I was talking about. Next example. Example, it's not example, is it example 4? Still example 3, part C. Okay, so we want to look at the conversion of a sulfate into sulfur dioxide. SO4 2 minus to go to SO2. Again, number 1, check atoms. I'll start with sulfur. I've got 1 sulfur on the left. I've got 1 sulfur on the right. Sulfur is balanced. Oxygen is not balanced. I've got 4 oxygen on the left and 2 oxygen on the right. So that means I need 2 H2O. Let me just move this. Sorry. Okay. To add H2O to balance the oxygen atoms. If I introduce H2O, that means I'm also introducing hydrogen into this equation. 4 hydrogen on the right must be followed by 4 hydrogen on the left, except that the hydrogen that we're adding is H+. Atoms done. So that's step number 3. Add H+ to balance hydrogen atoms. Next is the charge. Looking on the left, we have -2, 4 H+. That means each hydrogen ion carries a +1 charge. But since there are 4 of them, we say it's 4 lots of +1. Next, on the right side, SO2 is neutral. H2O is also neutral. Therefore, there's 0 charge. To balance off the charge, at the moment I have -2 plus 4. So that's +2. I want to bring this down to 0. All I need to do is add 2 lots of electrons. So then it becomes 0. add electrons on the left to bring down the charge to 0. So now you have both total charge 0 on the left and the right side. I wonder if this is given to you in the okay. So it's given here in your data booklet, SO4 2 minus plus 4H plus 2E minus to form sulfur dioxide plus 2H2O. And the working or the method to work out that half equation is by first balancing the number of atoms and then balancing the charges on both sides. Next is the, what else? Oh, I just wanted to point out that this is reduction. It is a reduction process because sulfate has gained electrons, 2 electrons to be more specific, okay? And if we want to talk about the oxidation state, sulfur would be -2 plus 8 plus 6. So that's the oxidation state. And then in SO2, it would be +4. Again, there's a reduction in 2 units because you have gained 2 electrons. And the bottom part is charge, so you don't get confused. It's easy, okay? It shouldn't take you like 5 minutes to write down a half equation. Moving on. Combining half equations to get ionic redox equations. So we're now going to combine our half equations to get a full, complete equation, whether it's neutral, uncharged, or ionic equation. The most important thing is that when we combine half equations, the first rule is that one half equation must be oxidation and the other half equation must be reduction. That's why it's called a redox. You cannot combine two half equations that are both reduction or both oxidation. Another thing is that in an equation or in a reaction, the number of oxidation must be followed by the same number of reduction. What do I mean by this? Okay, any increase in oxidation state must be accompanied by the same decrease in oxidation state. So this means that if species A is being reduced by 5, which means it gains 5 electrons, the other species B, must also lose 5 electrons. Okay. So here is example number 4, where we are already given the fully balanced half equation, reduction of manganate and oxidation of C2O4 2-. Okay, they're all balanced. When we want to combine them, it's actually quite straightforward. You just add them all up in such a way that all reactants add up and then all your products add up. But first, before you do that, you have to make sure that the number of electrons are equal. As I said just now, if manganate is being reduced by gaining 5 electrons, C2O4 2- must also release 5 electrons. So this time we're going to manipulate the number of electrons by multiplying the equation, right? So we look at this, we've got 5 electrons on reduction and 2 electrons on oxidation. So you want to find a common factor between these two. The common factor would be 5 by 2, right? Which means 10. So what we can do is we multiply. When we multiply electrons, we can't just multiply the electron alone. Otherwise, you'll mess up the balancing. The charge will no longer be balanced. So what you can do is when you want to multiply your electrons, you multiply the whole thing. So if I multiply the whole thing by 2, I should get 2 MnO4 minus plus 16 hydrogen ions plus 10 electrons 10 electrons to form 2 manganese 2 plus ion plus 8 H2O. So I've got 10 electrons for my half reduction equation. My half oxidation equation, if I want it to match my reduction, I have to multiply it by 5. Sorry, the text is in the way. So multiplying by 5 should give me 5 C2O4 2 minus to give out 10 carbon dioxide plus 5 electrons. Now, do you notice, not 5, 10 electrons. Plus 10 electrons. Do you notice that in my reduction, electrons is on the left side? For my oxidation, electrons is in the right side. Why do I point this out? Is because you're about to see the next part. So what's going to happen? It doesn't matter who you put first, but I like to deal with one half equation first and then followed by the other. So as I said, write down all your reactants on one side. MnO4 minus plus 16H plus 10 electrons plus 5 C2O4 2 minus. That's all your reactants. Double check again. Reactants reduction, reactants oxidation. Products 2 Mn2 plus 8 H2O plus 10 carbon dioxide plus 10 electrons. Next is to simplify your equation. You've got 10 electrons on both sides. They cancel out. Okay. What else can you do? MnO4, H plus, Mn2 plus, H2O. Okay, everything else cannot be simplified or cannot be cancelled out anymore. So your final equation, this is ionic because we've got charges, is this. That's all. That is your redox equation. They're balanced. As long as your half equations are balanced, your full equation will be balanced as well. All right. Imagine if you were to balance this, it would be difficult, right? So that's why I tell you always make sure your half equations are balanced first and then only you combined. Okay, if you want to copy this down, you can stop the video here and then move on to the next example. Example 5, you have sulfate being reduced to H2S. And in the oxidation side, you have the iodide ion to be oxidized into the iodine ion. Okay. Now, before you can combine these two half equations, you have to make sure that the number of electrons are equal. The reason is because you want them to cancel out later on. A full redox equation does not contain electrons. Perhaps I could add that on. A full redox equation, whether it's uncharged or ionic, should not have electrons in them. If you still have electrons, that means it is not balanced. Okay, right. So I've got 8 electrons being gained, but 2 electrons being lost. That doesn't match. And that tells me I need to multiply my oxidation half equation by 4 so that I get 8 iodide ion to form 4 iodine plus 8 electrons. Now that I'm happy both of them are the same, I can start writing down, combining them by writing down the reactants on one side and the products on the other side. So I've got SO4 2 minus plus 10H plus 8 electrons plus 8 iodide to give you H2S plus 4H2O plus 4 iodine and 8 electrons. The only thing that you can cancel here is the electrons. That means for this reaction, you need 8 lots of iodine to react with actually, why do I change the, I should keep it as the, should keep the position. Sulfate in acidic condition will react with iodide ions to form H2S plus 4H2O plus 4 iodine. The equation should be balanced. The charge should be balanced. Another thing that I want to point out is the species that is being oxidized. Okay, first we look at the reduction. The element that is being reduced is actually your sulfur, not oxygen. Okay, if you remember to work out the oxidation state or the oxidation number of sulfur, you should find that it is +6 in SO4 2 minus oxidation number, and then in H2S it's -2. Okay, so going from, okay, I'll leave that for now. As for iodine, the oxidation number is -1, but you've got 8 lots of that. And in iodine, I2, it's 0. Okay, now I'm going to put that information here. SO4 2 minus 2H2S, that means you go from +6 all the way to -2. You have dropped or decreased your oxidation number by 8 units. Why is it 8? 6 to 0 is 6 units. 0 to -2 is another 2 units. So in total, 8 units. As I mentioned just now, the decrease or increase in a reaction, the same reaction, has to be followed by the same increase. That means we have to make sure that our iodide is also being oxidized by 8 units. That means it has to increase by 8 units. Okay, let's see. We've got I minus to go to I2. Each iodide is -1. And since there are 8 iodide ions, I multiply it, it's -8. Each iodine in I2 molecule is 0. And there are 8 of them. Okay, we're talking about the iodine atom. Got 2 and 4. So can you see that the increase is from -8 to 0, increase by 8 units. So this is what redox reaction is. The increase or decrease must be followed by the same unit, same number. Okay, please copy that down. By looking at the oxidation number in a species of a reaction, this means that we can use this to balance redox reactions. Okay, how? In case they don't give you the half equation, they just give you a full equation, ionic equation, but then they want you to find the balancing. Sometimes counting the number of atoms will be time consuming. So what you can do is by looking at the oxidation number. Okay, oxidation numbers can be used to balance chemical equation. Roman numerals, so I've talked about these Roman numerals already, that they indicate the oxidation number of that element. Okay, so I will not be talking about that. Next, so this is assuming that I do not have access to half equation, right? So I'll just follow the question as it is. Manganate 7 ions, M and O4, I'll use a different color. M and O4 minus ions will react with Fe2 plus ions in the presence of H plus. Maybe I'll give space for balancing. Okay. To form Mn2 plus Fe3 plus ions plus H2O. So these questions want us to find the stoichiometric number by using oxidation state. So those are the missing information at the start, the mole ratio. Okay, basically it's just the mole ratio. Okay, first we need to identify who is being oxidized and who is being reduced. I think the easiest one to see is Fe2 plus. Yeah. So Fe2 plus to Fe3 plus is, let's see, maybe I want to use a different color. So going from Fe2 plus to Fe3 plus, that is an increase by 1 unit. Yeah. At the moment is 1 unit, but we know that it depends on how many moles of Fe there are. So we're just going to write down +1. Okay, X lots of +1. And we know that this will be, of course, an oxidation. The other possible half equation or the other possible half reaction would be the decrease. Well, it has to be a reduction, right? You cannot have an oxidation with another oxidation in a reaction. So manganese, here it's +7. Oh, I should have written that down. Let me just write that down. It's +2 here, and then it's +3. That means oxidation is increased by X lots of +1. Manganese is going from +7 to +2. All right, so this +7 to +2 is Y lots of 5. That means this is reduction, -5, since it's a decrease. It is a decrease in oxidation number. Okay. Next, we want to match. Okay, so there's 5 and 1, right? The common factor would be 5 by 1, which is 5. That means I have to match so that my oxidation is increased by 5. My reduction is decreased by 5. Remember, the X indicates the number of Fe atoms. Because we're here to find the mole ratio or the stoichiometry number, right? Now, if I change X equals to 5 moles, okay, that means my oxidation is now, plus 5. And my reduction is also minus 5. They match. Oxidation numbers go up by 5. Oxidation number goes down by 5. That means Y must be 1. And I only have 1 mole of manganate to form 1 mole of Mn2+, whereas my iron, I need 5 lots of Fe2+ to be reduced to, to be oxidized to 5 lots of Fe3+. Okay, so now if I correct my diagram, 5 times of +2, which is 10, to go down to go up to 5 times +3, which is 15. So you go from 10 to 15. That is an increase by 5. So now it matches. Goes down, goes up by 5, goes down by 5. Okay. The rest, you just have to follow the equation. Oxygen you have on the left. You only have oxygen on the left. So maybe after you balanced the reduced and oxidized species, balance all other atoms. Okay, so I've got 4 oxygens on the left side, so I need 4 oxygens on the right side. Now I have to balance my hydrogen. I only have 8 hydrogens on the right side, so my H plus should be 8. Okay, so 1 is balancing the oxidized and reduced species. Secondly, balance oxygen by playing with H2O. Okay, and lastly, balance hydrogen by playing with H plus. Now you may argue and say, why are we balancing it in a difficult way? Why can't we just do the counting, the number of atoms on the left and the right side? Now I can tell you that this will take you forever to balance. I can assure you, because these numbers are like 1, 5, 8, 1, 5, and 4. The easiest way is to use oxidation number, okay? And sometimes only oxidation number can help you balance the equation. All right. Okay, you can pause here if you want to copy this down. Next, we are going to look at a type of redox reaction called disproportionation. Disproportionation is a reaction in which the same species is both oxidized and reduced. Now, when I said the same species, means the same formula, but different atom. So here is an example. When chlorine reacts with water, H2O, it forms HCl and HClO. Now you notice that there are 2 atoms of chlorine. So one atom will be oxidized. In this case, this one, oxidation, okay? And the other chlorine atom will be reduced. That's why it is extremely important for you to know how to work out the oxidation number. Because without knowing how to calculate the oxidation number, it will be difficult for you to determine who has been oxidized and who has been reduced, okay? So this is an example of a disproportionation reaction in which the same species, in this case, the chlorine molecule, but different atom. Please make sure that you mention different atom. One atom is oxidized and the other is reduced, right? Next example, balancing disproportionation reactions. Balance the disproportionation reaction which takes place when chlorine is added to hot concentrated aqueous sodium hydroxide. The products are chloride, ClO3 minus ions, and water. Okay, so that's the only information that I know. So I've got chlorine, Cl2, plus okay. All right. So I repeat what I was saying, just in case there was no sound just now. I think it says I'm muted. Okay. So if I follow the question, it says that chlorine reacts with sodium hydroxide. Okay, I repeat, to form chloride ion, Cl minus, chlorate ion, ClO3 minus, plus H2O. Okay, so what happens? If you notice that sodium is only present on the left side, and on the right side, there's no sodium. Now, sodium hydroxide is an ionic compound. So it is actually made up of Na plus and OH minus ions. Sodium can be omitted out because it is a spectator ion. It does not get reduced. It does not get oxidized. All right. So to simplify, we can just deal with this chlorine hydroxide ion as our reactants, chloride and chlorate, and also water as our products. Okay, so what do I want to do next? I want to balance the disproportionation reaction by using oxidation numbers. So that means oxidation numbers must increase and decrease by the same amount. Okay, so let's have a look. This is a disproportionation reaction, which means the same species, which is Cl2, being oxidized and being reduced as well, but different atom. Okay, so we look at the first atom, that's the easier atom. I'll use a different number. Chlorine, Cl2, to go to chloride minus. So Cl2 is 0. Okay, 1 chlorine atom to go to -1. So that looks like a reduction. Yeah. Next, but still, I don't know how many chlorines there are. So I would just write it as -1 times X. Next, same, the other chlorine atom goes to ClO3 minus. So the other chlorine atom has an oxidation number of 0 in Cl2. And in ClO3 minus, if we just do that quickly, 3 times -2 -1, chlorine should be +5. Yeah, -1 plus 6 will be +5. So that means this is +5. So that's an increase by Y lots of 5. I want to match them together. So the common factor of 1 and 5 is 1 by 5. That means I have to multiply it by 5. Okay. So how can I multiply this by 5 is taking my X to be 5. X is now 5, so that I have 5 lots of chlorine. Okay. Okay, in this case, it's easier to write down 5 chloride ions first. Okay. Next, we want to balance our, what can we balance next? Our oxidation number is already balanced, goes up by 5 and goes down by 5. So that means if X is equals to 5, I can erase this to become 5 times -1, right? Next, do we count oxygen? Do we count hydrogen? I feel like it's easier to balance the charge first. So number 1, what we did just now, balance change in oxidation. Next is the charge. I don't have space. I'll just do this. At the moment, I have -1 on this side. And on this side, I've got -1, but 5 times plus -1. So -5 -1, so that's -6. Okay. And I've got -1 on the left side. To make it to be -6 on the right side, a left side as well. So I don't want to add anything on the right side. Okay, I'm not adding electrons. You only add electrons to half equations. This is not half equation. This is a combination. This is a full equation already. Okay, so to make the left side 6 as well, I need 6 lots of hydroxide. Okay, so it's a little bit tricky for this one. So that means my charge is now balanced. Okay, balance charge -6 on both sides. How? I just added 6 moles of hydroxide ions on the left side. Okay. Next is counting the number of oxygen and hydrogen, because on the left side, I've got chlorine, oxygen, and hydrogen. So I know that I've only got 6 oxygen and 6 hydrogen. The easiest one is hydrogen. 3 hydrogen should make up 6. Next is oxygen, which turns out nice. 3 oxygen plus 3 oxygen, 6 oxygen. Now I want to balance my chlorine. I've got 5 chloride and 6 chlorine. So altogether, I need 3 Cl2. Okay, so that should be the balance equation. Part 3, just now, what did we balance? Balance O and H. They should have 6 O's and 6 H. And lastly, balance Cl atoms. There should be 6 Cl atoms on both sides. Okay, it's not an easy one, but it's much better and faster, I think, rather than counting the number of atoms. Okay, if you want to copy this down, you may pause here. Okay, example 8, write down the ionic equation of the following reaction by combining the half equations. Potassium dichromate solution acidified. So that's potassium Cr2. Dichromate is Cr2O7 2-. So that's K2Cr2O7 plus acidified dilute sulfuric acid, H2SO4. Later, you can see that these equations can actually be simplified. Okay, it's used to oxidize ethanol, CH3, CH2OH, to ethanoic acid, CH3, COOH, with itself being oxidized to chromium ions. Okay, this one, I think it's easier for us to deal with half equations. Where we have one side of the chromium, because we know chromium is being reduced to Cr3+, and then our ethanol, CH3, CH2OH, is being reduced to ethanoic acid, CH3COOH. So we follow the strategy that we used earlier on. So I'm just going to erase this because I think that would be difficult to balance. So we use half equation. Okay. Cr2 to Cr2O7 to Cr3+. First thing, we want to balance the chromium. Balance chromium. I've got 2 chromium on left side. So on the right side, I need 2 chromium as well. I've got an oxygen on the left side, and there are 7 of them. So that means I need 7 H2O. Introducing 7 water also means that I have introduced 14 hydrogen. 14 H plus. Okay. And then lastly, I need to balance balance Cr, and then oxygen, and then hydrogen, and lastly, charge by adding electrons. Why can I add electrons? Because I'm looking at half equations. On the left side, I've got plus 14. On the right side, I've got plus 6. So here, plus 14. So that is a difference in 8 units. And what I can do is I add 8 electrons. So now I've got plus 6 on the left and plus 6 on the right. Okay, done. CH3, CH2OH, I count the number of atoms. So this time, my carbon is balanced. My oxygen is not balanced, right? I need water. I don't have space. Okay, let's do this. Maybe I'll put this at the end. Okay, I need 1 H2O here. So now I have to worry about my hydrogen. First, balanced carbon. Second, oxygen. Third, hydrogen. On the left side, I've got 3, 5, 6, 8 hydrogen. On the right side, I've got 4 hydrogen. That means I need to add 4 H plus on the right. Done. Charge. 0 charge. Here I've got plus 4. So I need to add 4 electrons to cancel out the charge to become 0. Before I can combine this, I need to make sure that the number of electrons are the same. So can you see that I need to multiply? So here I've got 8 electrons and here I've got 4 electrons. So I need to multiply my oxidation reaction, which is the loss of electrons, by 2. How do I do that? 2 times. Okay, that means if I copy this down on another page, okay, much better. I should have, paste. I should make this smaller. Okay, so I should have reduction. I know why, because my ink as Cr2O7 2 minus plus 14H plus 8E minus. There's something wrong because my Cr2O7 2 minus is missing here. Okay, sorry about that, 2 minus. So that means everything is not right, unfortunately. 14 minus 2 is 12. It should be plus 12 here. Sorry. Plus 12. And then I've got plus 6 on the right side. It should be plus 6 electrons. Sorry about that. So that means this is wrong. Okay. I repeat. Okay. After I have balanced my atoms, next I want to balance my charge. On the left side, I've got -2 plus 14. So that's plus 12. Okay. How do I know that? -2 plus 14 times plus 1, which is plus 12. On the right side, I've only got plus 6. So to balance this out, I need to add 6 electrons. So I'll just erase this. Okay. And then my other half equation, I've got plus 4 on the right side. On the left side is 0. So to balance out the plus 4, I need to add on 4 electrons. Okay, now before I want to combine these two half equations, notice that the number of electrons are different. Okay, they are not the same. So the common factor between these two is 12, right? So I have to multiply this by 2 and then the other one by 3. So if we multiply, just check again that all your atoms, carbon, oxygen, hydrogen, chromium for the other equation, and then also your charge. It's most important, okay? After you balance your charge, you multiply them so that the number of electrons match. The equation on the left is representing reduction because you gain electrons, and the equation on the right is oxidation because you lose electrons. So when we combine reduction and oxidation, combine half equations, this is where we get rid and ox. Okay, so redox reaction. But make sure that the number of electrons are the same first. Okay. When you change the number of electrons, you have to multiply the whole thing. Otherwise, you will change the balancing. Likewise, for the oxidation half equation, multiply everything by 3. So after you multiply them, combine them, you should get 3 lots of ethanol plus 2 lots of dichromate ion plus 16 H plus 6 times 2, 12 electrons to form 3 lots of ethanoic acid plus 12 electrons. And then you also add the products from the reduction equation. 2 times 2 is 4 Cr3 plus 7 times 2 is 14. Is that correct? 7, yes, 14 H2O. Okay, so just look at both sides. If there's anything that you can cancel, the electrons should cancel out. Otherwise, you would get CH3, CH2OH plus 2 lots of dichromate ion plus 16 H plus to form 3CH3COOH plus 4 chromium ion plus 14 H2O. Okay. Right, just one last thing. Okay, I don't have the question, but you have the question. I want you to look at question. Oh, it's here. Okay, so this question is probably one of the more difficult questions of MCQ. Okay, so let's read. A 10 centimeter cube sample of 0.30 mole per dm cube of thallium Tl plus NO3 minus required 20 centimeter cube of 0.10 mole per dm cube of acidified ammonium VO3 minus. Okay, to oxidize it to thallium 3 plus. Vanadium is the only element reduced in this reaction. Okay, so what's happening here? The easiest way is to start with half equation first. Half equation based on the information given. We know that TL plus would go to TL3 plus. Okay, but we still don't know how many thallium, the number of moles. And this looks like an oxidation reaction to me. My oxidation reaction is not balanced, okay? TL plus NO3 minus, I can break them down into TL plus and NO3 minus. I just focus on thallium because that is the species that is being oxidized, okay? The other half equation would be reduction, where I'm going to reduce, my vanadium in VO3. So again, this can be broken down into NH4 plus and VO3 minus. Now I just want to focus on the vanadium. So vanadium would be -1 plus 6 plus 5. Okay, so VO3 minus is actually my vanadium that has an oxidation of +5, right? So I'm going to write something that is not accurate. My vanadium is +5, this is not an ion. This is just a species of vanadium atom with oxidation number of +5. Okay, that is not an ion. So we know that vanadium starts from +5 and reduced to, that's the question. What is the oxidation number of the vanadium in the reduced form? So vanadium will be reduced to a number X. Okay. In full equation, but not balanced, full equation, please bear in mind they are not balanced. Same for the half equation, not balanced as well. Right? We want to find the mole ratio of reaction of thallium with VO3 minus. Okay? To find the number of moles of thallium, we take 0.3 moles per dm cube as the concentration and the volume. Concentration of thallium versus volume of thallium, 0.30 times centimeter cube must be changed to dm cube. (0.01 dm cube). So that's 3 times 10 to the power of -3 mole. Why do I find the number of moles? Because I want to know the mole ratio. Number of moles of vanadium is 0.1 mole per dm cube. I'll start with concentration times volume. So concentration is 0.10 moles per dm cube times by 0.02. So that's 2 times 10 to the power of minus 3. So that means what this number tells us is that the mole ratio of thallium plus and vanadium VO3 minus, or my vanadium with an oxidation number of +5, is 3:2. Okay, so if I write down the full equation using a different color so you don't get confused. Thallium plus reacts with vanadium +5 in a mole ratio 3:2 to form 3 moles of thallium 3 plus and 2 moles of vanadium X. We do not know the charge, we do not know the oxidation number of the vanadium. Okay, so we know information about thallium. So let's see. Thallium goes from 3 lots of +1 to 3 lots of +3. So that's an oxidation or increase by 6. Yeah, increase by 6. That means the vanadium must also decrease by 6. This means vanadium must decrease by 6. Okay, our starting point, we've got 2 plus 5, so that's +10, right? We want it to decrease by 6. So what must 2x be, right? So 10 minus 2x should be -6. Okay, and x, is that correct? -6 minus sorry, it should be just 6. Okay, if you add on the sign, it will be wrong. Okay, so when 10 minus 2 lots of x, it should be 6 because we want it to match with our oxidation. Okay, our reduction must also be 6. So that means this is 6 minus 10 is -4 divided by -2. So x is +2. That's how you find the oxidation number of x. If you work this out, if you put x into here, you will see that the reduction and the oxidation match. It increases by 6, decreases by 6. The only thing that's difficult, the extra step here, is to find the number of moles to balance the atoms. Okay, so that's quite a lengthy process, but if you don't understand it now, just make sure you copy it down. I don't know if you are able to see this in your screen, but I have to do it really small. Okay, I know this lesson, this video overshoots, but that's the only way for us to finish our syllabus before December. Okay, so thank you very much for your attention. Don't forget, after this, please answer questions in Microsoft Forms. The link can be found in the description box. Okay. Assalamualaikum and thank you.